Hello everyone, my name is Alex. I'm a fifth year engineering physics student at UBC and the captain of the UBC Solar Car team. Today we will be talking about motors with a focus on brushless DC motors and magnetic circuits. I will be walking you through some of the theory and background required for you to design your own motor, and we will look at a few aspects that make solar car motors more unique than the rest. We will pay special attention to the different kinds of power losses that reduce efficiency, and briefly touch on a couple other aspects that one could look into for their design depending on their application. Now, with that bit of introduction out of the way, let's dive right into it and we'll talk about motors and magnetic circuits. As a recap, motors are used to convert electrical energy into rotational motion. The applications of this technology are limitless, used in everything from computer hard drives to 3D printers to robotic motion. There are several different kinds of motors that utilize both DC and AC power. Most of what will be discussed in this talk applies to most of these motor types, with the exception of the brushed DC motor, which has a very different theory of operation. This one we will not focus on very much. In general, most motors operate in a relatively simple way. They use a magnet to spin another magnet. The electrical conversion aspect comes in when we start using wires and electrical current to create an electromagnet, and by doing so we have more control over the direction and the speed of rotation. We usually refer to the wires as the coils, and the magnets are known as the poles. The term pole is used because not all motors use permanent magnets, as in the case of the AC induction motor. In other words, it's a more general term for the part of the motor that is being rotated. As we'll discuss in more detail later on, there's a fundamental relationship between the number of poles and how much torque can be produced by the motor, as well as how fast it spins. The part of the motor that rotates is referred to as the rotor, and the part that is stationary is called the stator. Each motor type can come in various architectures. Here we will only focus on the in-runner and out-runner architectures as they're the most common. With an in-runner, the magnets are inside the coils, and so the inside of the motor spins. With an outrunner, the coils are in the middle, so the outside of the motor is the part that spins. The different architectures each have their own benefits with regards to mass, cost, ease of manufacturing, and also technical performance. The choice really depends on the application, so later on we'll go into a little bit further detail about some of the trade-offs. Now we're going to focus a bit more on the main type of motor for this talk, the brushless DC motor. Brushless DC motors, or BLDC motors for short, are among the most common types of motors because they offer a very wide range of utility. They can be very efficient, very fast, can produce very high torque, and are relatively inexpensive to produce. Overall, they are the most versatile type, whereas the other types are used for more specific purposes. For example, the AC induction motor is used for very high power applications, but tends to have very poor efficiency. Brushless DC motors are based around the idea of using feedback to determine the instantaneous angle of the rotor. With this, a controller then interprets the readback to determine which coil should be energized next to further rotate the rotor. The most common way to provide this feedback is by placing a digital Hall effect sensor on the stator, which detects the polarity of the magnetic field closest to it. With this, it can determine if the sensor is next to a north or south pole. Utilizing 3 of these sensors can allow the controller to essentially triangulate the exact position of the rotor up to a certain angular accuracy. This algorithm is known as the commutation sequence. In some cases, magnetic resolvers are used instead of digital Hall effect sensors because they offer better noise immunity, but these devices are more complex and expensive. The portion of the BLDC motor that handles this commutation sequence is usually called the motor controller, though other names are sometimes used such as the ESC, electronic speed controller. The motor controller has 2 main portions, a DC to 3-phase AC power converter, sometimes called the inverter, and a microcontroller used for handling all the main logic. As we can see from this, a brushless DC motor isn't actually DC. It just takes a DC input and then converts it back to AC. This shouldn't be all that surprising, as the motor requires a continuously oscillating input in order to provide the rotational output. As one can probably guess, the output of the inverter is never a true sine wave, but rather a high-frequency combination of DC steps that emulate the operation of an AC signal. The microcontroller uses a PID algorithm to control the speed at which the inverter MOSFETs switch on and off. The fact that each of these 3 phases has 2 MOSFETs gives the ability to change the direction of rotation. We won't go much deeper into the motor controller in this talk, since designing one can be an entirely separate design task. The motor controller produces this pseudo-AC power signal with a certain frequency. This frequency causes the rotor to spin at a constant speed related by the number of poles. We usually refer to the input AC frequency as the electrical frequency, omega sub E. We then say that the rotor spins with an angular frequency omega sub R, given by omega sub E times 2 over P, where P is the number of poles. The factor of 2 comes from the fact that the rotor is symmetric, and thus the important factor in the speed is the number of pole pairs. I mentioned previously that a motor with more poles will have more torque and less speed, and this is where that statement came from. For constant power and all other variables, including things like size being constant, more poles will cause the motor to operate at a slower speed and thus output higher torque. This is also why high torque motors often have lots of magnets. Another fundamental relationship is the linearity of torque with respect to current. Note that the current is AC, but the current used in this equation is more like the DC current, as it's transformed into something called a rotating reference frame. This is a completely separate topic that we won't go into a lot of detail here, just focus on the high-level concept. More current will give proportionally more torque. The variable K is sometimes called the torque or motor constant, and is related to the number of poles and the strength of the magnets. We're now going to turn our attention away a bit and talk about motors as magnetic circuits. Before we do, we should refresh a little bit about electrical circuits. When we talk about electrical circuits, one of the earliest concepts introduced is that of resistance, the opposition to the flow of electrons. Resistance is fundamental to any real conductor that's used in a circuit. When we look at the simplest case of the resistance of a wire, we find that it's entirely based on the geometric and material properties of the conductor. The resistance is directly proportional to the length of the conductor and the resistivity of the material, and inversely proportional to the cross-sectional area of the conductor. This is why thick copper cables are used for transmitting large amounts of power. The copper provides a very low resistivity, and the thick cable gives a very large cross-sectional area. It turns out that when we talk about magnetic circuits, there's a very similar concept known as reluctance. Magnetic circuits also require conductors to transmit the magnetic field, and these conductors still have a certain opposition to this. There's a little bit of a difference between resistance and reluctance, and it can seem like a bit of a nuance. While electrical resistance dissipates energy away as heat, reluctance instead stores the energy in the magnetic field. The exact way that this works quickly dives into the quantum realm, and even some experts still don't entirely agree about where this comes from. But our main takeaway here is the analogy between resistance and reluctance. Even the governing equation is very similar. The reluctance, which we write as this curly r, is proportional to the length and inversely proportional to the cross-sectional area of the conductor, as well as another material property called the permeability, which we write as this letter mu. When we talk about electric circuits, we more normally talk about the ideas of current and voltage, the things that we measure and experience. We talk about current as the thing that flows in the circuit. The magnetic equivalent of this is referred to as magnetic flux. It's the density of the magnetic field in a conductor. Nothing actually moves, so it's a bit more abstract. The equivalent of voltage, which is formerly known as electromotive force, is this thing that we call the magnetomotive force. We represent flux with a capital phi and the magnetomotive force with a capital F. The magnetomotive force is the thing that we use to relate the magnetic and electric circuits. When produced by a coil with N turns and current I, the magnetomotive force produced is given by F equals N times I. This concept may seem unfamiliar, but just think of F as the voltage, and instead of being produced by a battery, it's produced by a coil. In electric circuits, we usually talk about electrons flowing, like there's something that physically moves from one conductor to the next. In magnetic circuits, this is not exactly the case. Instead, we talk about something called magnetic domains. The spin of each electron in the material acts like a tiny bar magnet, and when the magnetomotive force is applied, these bar magnets all align in order to create the magnetic field in the material. As a bit of a summary, here are a couple more things that tie the analogy together. With electric circuits, we commonly refer to Ohm's law, V equals IR. The same thing applies in magnetic circuits with F equals R times phi. With electric circuits, we find that the current takes the path of least resistance and the same applies with magnetics as well. Flux always takes the path of least reluctance. As a bit of a side note, I also wanted to quickly touch on the concept of inductance, as this is another tie-in between electrical and magnetic circuits. In reality, a coil and an inductor are the same thing. We can talk about the voltage across the inductor being L times di dt. Going back to Faraday's law, we also know that the voltage is equal to N times d phi dt. This gives us a relationship connecting inductance, current, and our magnetic flux. When we combine this with our magnetic equivalent of Ohm's law, we see how reluctance and inductance are related. Recall earlier that we mentioned F equals N times I as the definition of the magnetomotive force. Now that we've got the fundamentals of magnetic circuits down, let's actually look at a motor and see how it all ties in. There are a few definitions that we can quickly observe. The coils of the motor act as the source, the thing that provides the magnetomotive force, or voltage. The magnets act as the load, being the parts that actually require energy to do work. In this case, the work is physical motion. In terms of conductors, we have a few new parts to introduce here. The stator is made of steel that we usually refer to as the core or the iron. This includes the part that the coils wrap around. On the backside, the magnets themselves are usually glued to something called the back iron. Lastly, the space between the stator and the rotor is called the air gap or the flux gap. The core, back iron, and air gap are all the conductors of the magnetic circuit. They create the flux path from the source to the load. The main challenge of designing a motor is to optimize these conductors as best as possible while still considering things like size, mass, temperature, and cost. The stator can be further broken down into a few subsections. The cutouts where the wires go are called the slots, and the remaining T-shaped portions are called the teeth. The remaining round portion closer to the center is called the yoke. Usually when we talk about the stator, we discuss the size of the yoke, the number of teeth, and accordingly design the size of the slots. We discussed earlier about the ideas of reluctance and resistance, and right away we can see a major trade-off when designing the stator. If we have bigger teeth, we will have more cross-section in each one, and thus have less reluctance. At the same time, larger teeth require smaller slots, meaning that only smaller wires will fit. Smaller wires have less cross-sectional area and thus have more resistance. We'll keep coming back to this idea throughout the rest of this talk. The rotor is similar, but far simpler than the stator. Because there are no coils on the back iron, there's not as difficult of a trade-off. Here we just optimize our flux path reluctance while still being cautious of things like size and mass. The air gap is among the more conceptually difficult portions. We mentioned that the air gap is the space between the stator and the rotor. This emphasizes a key difference between magnetic and electric circuits. In an electric circuit, it is very difficult to pass current through air. However, in magnetics, it's not as difficult to pass flux through air. As a result, the air gap has a property called flux leakage, a small portion of the flux in the air that escapes from the motor. For this reason, a smaller gap is always better. Something to be cautious of is the fact that a rotor size is not entirely constant. As the rotor spins, a centrifugal force will create a strain on the motor, causing it to expand. On an outrunner architecture, this will cause the air gap to increase, meaning that you will lose more energy at high speeds. The inrunner is much more dangerous. At high speeds, the centrifugal strain will decrease the air gap. If the nominal air gap is too small, this change can cause the rotor and stator to collide, which can severely damage the motor. An additional design aspect that we'll only briefly touch on is something known as a composite sleeve. This is usually added on motors designed for very high speeds, where the centrifugal force on the rotor can significantly affect the air gap size. Materials like Kevlar or carbon fiber provide a very high tensile strength around the rotor to limit the centrifugal expansion. Cogging torque is the result of the magnets on the rotor pulling on the ferrous material of the stator. This creates a resistance to motion even when the motor is not powered, where it can quote-unquote click from pole to pole. As a result of cogging, the output performance of the motor is also subject to something called ripple, which impacts the torque, speed, and current. Though we talk about these factors as if they are constant, cogging induces a small oscillating component to each one. These are generally not extremely detrimental for performance, but they can increase vibrations and noise of the motor, and can cause very coarse motion at low speeds. This can be an issue for machines used for fine movement like robots. One way to minimize cogging and ripple is to skew the slots of the stator, as shown here. This skewing eases the transition from pole to pole, as the transition is slightly more continuous rather than having the original discrete steps. However, slot skew can be hard to manufacture as it can complicate the assembly of the main stator core. We now know that the motor spins by applying an AC current through the coils. However, the same thing actually happens in the opposite direction too. As the rotor spins, the magnets produce an AC voltage in the coils known as back EMF. All of this comes from Faraday's law of induction. This voltage is proportional to the speed and magnet strength and has the same electrical frequency omega sub E. The back EMF of the motor is subject to several harmonics due to the symmetries of the stator. Different winding configurations can change the magnitude of these harmonics and change the shape of the back EMF as well as the ripple. There are many different winding patterns to choose from. A common one for the solar car motors is the DLRK pattern, which produces naturally high harmonics and can reduce ripple. The best winding pattern is application dependent. As a bit of a summary of the circuit, we can refine our original statement about what motors do. Motors take in energy through an electrical circuit and then convert that energy into a magnetic circuit whose output is mechanical motion. Now, with our understanding of the magnetic circuit out of the way, we can start to talk about the process of designing a motor. Displayed here is a giant map of all the different aspects of a motor. Right off the bat, we can see that there's a huge list of topics, and it may seem quite daunting. We'll go through a good portion of these in fair detail, but we won't get through everything. As we work through this pyramid, the topics covered in a good amount of depth will be marked blue, and some will be marked yellow just to indicate that we briefly touched on them. The next portion that we're going to talk about is the different metrics of performance, and this will guide us through how we actually design a motor. When we start a design, we need to understand our goals and how we're going to evaluate how well we met them. What are some of the different operational criteria? Some of the key things are listed here, such as torque, speed, power, efficiency, temperature, and so on. In most cases, the key requirements for the design will be torque, speed, or both. This will vary depending on your application, but for this talk, we'll keep our focus to solar electric vehicles. For this, our most essential metric is the torque output. We want to first determine the maximum continuous torque required. In the case of the solar car, this occurs when we are driving up a hill. Here, we pull out our first-year physics textbook and draw a free body diagram of the car, highlighting the key forces to consider. We need to know things like the vehicle's aerodynamic drag force, D, the rolling resistance force, R, and the gravitational weight of the car, W. To know all of these, we have to consider the steepest hill that we will drive on and set our desired specifications for our speed and acceleration when driving up that hill. We can write out Newton's second law, F equals ma, to determine the tractive force, capital T. This is equal to our torque output, tau, divided by the wheel radius, r sub w. With these very basic calculations out of the way, we can determine the torque and our speed, and multiplying these together gives us a power rating. For a typical solar car, the power rating tends to be somewhere in the 1 to 4 kilowatt range, and for a regular car, this will be something like 500 horsepower or something around 400 kilowatts. This gives us an idea of the order of magnitude that we're talking about. There is a case where the solar car will require more than the torque specification. For example, braking static friction. Granted, in this case, we're at zero speed, and so our earlier analysis changes a bit in terms of what forces we analyze. But lucky for us, BLDC motors can temporarily exceed their rated output power, sometimes by more than even a factor of 2. We refer to this as the motor's peak power. The peak power of the motor is usually thermally limited. As we'll talk about, there are certain limits on how much flux can be held in any given magnetic conductor, and we'll also have to watch out for the temperature of the individual components. In many production-level electric vehicles like Tesla's, the motor will usually be accompanied by some kind of gearbox or speed reduction. This is usually the case because faster, low-torque motors are generally cheaper and easier to make, and thus a gearbox is required to increase the output torque. The key trade-off for the solar car is the major loss of efficiency, which tends to be upwards of at least 10% for a near-perfect gearbox. For solar cars, available energy is scarce and efficiency is everything, so most teams opt out of a gearbox and instead go for what's known as an in-hub motor. In this case, the wheel of the car is mounted directly on the output shaft of the motor. Here are two images showing a brief comparison. On the left, we have a Tesla helical gearbox used to reduce the roughly 15,000 RPM motor down to a more reasonable driving speed at around 1,000 RPM if we're just looking at order of magnitude. On the right side, we have a Cicero in-hub solar car motor where we see that there's no gearbox and no transmission. The rim of the wheel is mounted directly to the rotor. Once we have our torque specification, we can look right away at estimating a size for the motor. For this procedure, we will assume that we're looking at an outrunner architecture, though it applies exactly the same to an inrunner as well. We will also assume that we are talking about a motor with a fixed number of poles, a fixed stator inner diameter, and a fixed air gap size. Now the question is, how does the size of the rotor correspond to the overall performance of the motor? We can intuitively guess that if the rotor is larger, we will be able to fit larger magnets, producing a stronger magnetic field and thus permitting higher torque output. As it turns out, we can defend this intuition with a bit of relatively simple analysis. Let's consider the force exerted on the magnets by a coil with current I. If the stator has thickness L and the magnets produce a field strength B, the Lorentz force is given by F equals ILB. If we sum up all the individual forces, we can say that the force acts over the entire rotor, which has an area of pi times the inner diameter of the rotor times the thickness L. This is the area of the inner cylinder of the rotor. With a force and an area, we can somewhat arbitrarily define something referred to as the air gap shear stress, which we represent with sigma. We write the output torque of the motor as T equals F times R, where R is the radius, or half of the diameter. If we plug in all of our equations, we can then relate the torque of the motor to the diameter and the thickness of the motor. This equation can then be simplified a bit and written as 2 times our air gap shear stress times the volume of the rotor. As we already have our torque specification based on our mechanics, it's normal to simply select an air gap shear stress in order to gain a fully constrained relationship between the diameter and the height of the rotor. The air gap shear stress is usually selected from a table that depends on your application. Though this seems a bit hand-wavy, we can more focus on the high-level relationship and notice that torque and rotor volume are linearly dependent. Here we can see a few curves generated at different torque values, with a few specific brushless DC motors plotted as well. With the torque specification in mind, we can simply walk along the respective curve and select a length and diameter pair that suits our needs. In the case of an in-hub solar car motor, there's a maximum limit on the rotor diameter in order for the motor to fit inside the wheel. Additionally, the material usage will change depending on the diameter and length, which can drive cost. Now that we're starting to get into some of the important design principles of building a motor, it's a good time to talk about some of the primary power losses of the motor and understand how we can change our design to maximize our efficiency. Firstly, let's refer back to our electrical analogy and look at the simplest circuit possible, a battery-powered LED. From our basic circuit analysis courses, we know that a resistor is required in series to avoid blowing the LED. This is because the battery outputs more energy than the LED can handle, and so some needs to be dissipated away. In this way, the resistor limits the amount of power given to the LED, controlling the amount of energy used to do useful work. By Ohm's law, we know that if we increase the resistance, the LED will receive less current and therefore it will be dimmer. All of the extra energy is dissipated away by the resistor as heat. In magnetic circuits, we mentioned how the concept of reluctance is very similar to resistance. The major difference here is that reluctance stores energy, but does not dissipate it away as heat. The rest of the effects, however, are the same. If our stator core reluctance is not properly designed, we will have more energy stored and thus less used to do useful work, like creating torque on the magnets. For this reason, we always want to minimize the reluctance of both our stator core and our rotor back iron. There is another consideration, however. We know that wires used in electrical circuits have a maximum current capacity before they heat up too much and burn. In magnetics, there's another similar concept known as magnetic saturation. It is generally much more prevalent than wire current capacity. Any magnetic flux path has a maximum amount of flux known as the saturation point. At any point after this, any additional flux added to the path is dissipated away as heat, causing the material to rise in temperature very quickly. This is essentially the point where the material has stored as much energy as possible and cannot take any more. The saturation point of a magnetic conductor is a material property. It is more often given as a maximum magnetic field strength that the material can handle, usually given in units of Tesla or Gauss. It is therefore essential to ensure that the magnetic field strength in the stator and rotor never exceeds the saturation point. This is where our electrical analogy starts to break down a bit, as we're going to talk about other sources of efficiency losses. These losses come from all the different parts of the motor, including the magnetic and electrical circuits, as well as some of the mechanical design. The first type that we're going to look at is eddy currents, which can be a bit tricky to conceptualize. While the coil works to produce a magnetic field in the stator and apply a torque to the magnets, the now spinning magnets have the reverse effect and produce a current in the stator. These reverse currents are known as eddy currents. Though these are magnetic in nature, the efficiency loss is actually an electrical phenomenon, as the currents are subjected to electrical resistance of the stator, dissipating a certain amount of heat. The governing equation for this power dissipation has a bit more of a formality to relate it back to the magnetic circuit. We see that the power is linearly dependent on the volume of the stator, as this gives us a sense of the electrical resistance. It is also quadratically related to the maximum of applied magnetic field strength, the frequency, and the thickness of the stator, as these factors provide an idea of how much current is produced and at what frequency. Lastly, we throw in a material-dependent proportionality constant to tie all the units together. We see from this that the equation looks very similar to the equation for our power dissipated by a resistor, P equals R times I squared. As this is a power loss, we want to minimize it. When doing so, we have two options. We can either decrease the resistance R or decrease the current I. However, from Ohm's law, we know that if we decrease one, the other will increase to compensate and maintain the same voltage. So the question is, which do we do? It turns out that it's more efficient to increase the resistance and decrease the current due to the quadratic dependence on the current. One can analyze the situation in which the resistance is doubled, cutting the current in half. While our voltage of the system stays the same, the power dissipated is overall cut in half. So what's the best way to increase our electrical resistance? To do this, we use something called laminations. Laminations are very thin insulated sheets of metal that are used to form the stator and rotor. By doing so, we are able to dramatically increase the electrical resistance. But because the sheets are electrically insulated and not magnetically insulated, our reluctance remains mostly unchanged. The laminations provide a smaller cross-section, increasing the resistance in each sheet. The laminations are usually less than 1 millimeter thick and are typically bolted, glued, enclosed, or sometimes even welded together to keep the parts rigid. There is a significant trade-off with mechanical strength and cost. The thin laminations can be very delicate and easily bent or deformed. Additionally, while thinner laminations are always better, the higher piece count increases manufacturing costs. Depending on the application, it may be more valuable to use a slightly thicker lamination to save cost if efficiency is not a top priority. A question that usually comes up is how the laminations are insulated from each other. After manufacturing, each sheet is coated with a very thin layer of insulating varnish, of which there are many different kinds and classifications. Only certain insulation methods permit welding of the laminations, and though this does create an electrical conduction path, the weld bead is small and usually on the outside of the stack, meaning that the bulk of the material laminations are still insulated, maintaining the small cross-sectional area. Something else to consider is that these varnishes are thin, but not infinitely thin. A poor varnishing job can affect stacking factor, increasing the overall thickness of the part. The next type of loss that we'll look at is hysteresis, and this is related to reluctance. If we stretch our definition a bit and think of reluctance as a representation of the energy required to keep the magnetic domains aligned in a certain direction, hysteresis represents the energy required to change the direction of the alignment. The plot on the right is usually referred to as a hysteresis loop. Here, the horizontal h-axis represents our input field, which is related to the applied magnetomotive force. The vertical m-axis is the resulting magnetic field strength in the material, where ms refers to the saturation point that we went through earlier. The concept to grasp here is that when we apply a certain input h, the material has a certain resulting magnetic field m. When we remove the input h, the magnetic field in the material does not revert back to zero. The magnetic domains remain somewhat aligned. Therefore, we have to apply a stronger H field in the opposite direction to fully reverse the orientation. This additional H field strength is now an added input that is required in order to spin the motor magnets and perform useful work. Quantifying this energy loss comes from looking at the area of the hysteresis loop, which represents the work done to realign the domains per unit volume. Notice that the area of the loop is entirely material dependent, including the hysteresis constant nu and the saturation point of the material. Multiplying this area by the volume of the stator or rotor gives the total work required for the specific piece in question. We then multiply by the number of reorientations per second, or in other words, the frequency, to get a power loss. This frequency is the field frequency, which is the linear equivalent of the electrical frequency we talked about earlier, not the rotor frequency. The last thing to mention is that the reluctance of the circuit can actually be derived from the hysteresis loop. As such, the reluctance losses mentioned earlier are included in the hysteresis loop, and so there's no need to double count. In practice, the hysteresis and eddy current losses are grouped together and referred to as the core losses. Unlike eddy currents, the hysteresis losses do not have some nice electrical looking equation, and it's entirely material dependent. As a result, the only thing that we can do to minimize hysteresis losses is to select the best material. This introduces the idea of electrical steels. Electrical steels are metals designed to meet three properties: low reluctance, high resistance, and a small hysteresis loop. They are therefore referred to as steels, but they are actually different from common structural steel alloys used in mechanical applications. There are several kinds of alloys, but the three most common kinds are made of either silicone, nickel, or cobalt. Each of these categories includes a wide range of alloys that feature different amounts of the respective material. For example, a top alloy for motors known as Carpenter 49 is made of 48% nickel. In some applications where the flux direction does not change, such as transformers, these electrical steels can come as grain-oriented, meaning that the magnetic domains are somewhat pre-aligned. This can reduce reluctance, but increases hysteresis, making it not very desirable for motors. Here is a comparison of the three main electrical steel types. In general, the silicone steels have the worst magnetic performance, but are the easiest to work with and can be the most cost-effective type. Nickel is a bit more expensive and is normally used when hysteresis losses need to be minimized and saturation is not as much of a concern. This includes applications like low-speed, high-efficiency solar car motors where we are not operating very close to the saturation point. Finally, cobalt is the most expensive by far and is used only when a high saturation point is absolutely essential. This would include applications requiring extremely high torque where efficiency can be sacrificed. A nice side note about grain orientation is that in many of these electrical steels, the orientation can actually be visible to the naked eye due to the very large grains similar to the grains of a wooden log. Producing the material like this can only be done when the metal is made. The larger grains produced have fewer internal boundaries, producing a more continuous flux path, which helps further reduce reluctance. As with everything else discussed, there are trade-offs of these electrical steels. All three of the main types tend to be heavier than regular steel and are also weaker due to poor mechanical properties like tensile strength. Additionally, the flux paths are quite delicate and can be easily deformed by something like the clamping load of a bolt. This can locally increase flux density, creating local hotspots in the material. Special care needs to be taken when designing the motor to ensure that no parts of the lamination experience any significant mechanical loads, and any loads applied from the housing or structure are evenly and widely distributed. In other words, it is best to mechanically decouple the stator and rotor from the shaft loads. That just about covers magnetic core losses. We will now look at the other types of losses, starting with electrical resistance. Naturally, the wires of the coils have resistance, which dissipates heat as the current flows through. A good solution is to use bigger wires. However, there's an important design decision to be made here. In order to fit bigger wires, the slots of the stator must be larger. This decreases the size of the teeth, increasing the magnetic core losses. It turns out that the maximum efficiency is achieved when the electrical and magnetic losses are as close to balance as possible, while still avoiding magnetic saturation in the stator. When winding the coils around the stator teeth, one must also consider that not 100% of the slot can be filled. The wires have a certain packing limit due to the cylindrical cross-section, and the wires also require thick insulation to protect from short circuits and corrosion. Taking both of these into account, it is more likely that something like 60 to 70% of each stator slot will actually be filled with copper. To make matters worse, the coils deal with AC currents, meaning that we may have to worry about something called the skin effect. The skin effect is a frequency-dependent phenomenon where current density in a conductor builds up around the perimeter and falls off exponentially as you approach the center. This increases the effective resistance of the wire because the usable cross-sectional area is significantly reduced. We define a quantity known as the skin depth, sigma, to represent the distance from the outer perimeter that holds 63% of the current density. This 63% number comes from the common 1/e factor usually referred to when talking about exponential curves. It is the distance at which the current density is 1/e of its maximum value, if you want a more formal definition. Going through some algebra on this nasty expression for the skin depth, we can determine that the effective area of the conductor can be approximated as just the circumference of the wire multiplied by the skin depth. The effective resistance then uses the same length and resistivity as the quote-unquote regular expression, but with the new effective area substituted in. It also turns out that the skin effect is the main reason why high voltage lines on the local power grid are transmitted as DC rather than AC. While we can't prevent the skin effect, we can minimize it. Think about it this way. If all of the current is transmitted in the skin of the wire, then our best solution is to just add more skin. To do this, we usually use a type of wire called Litz wire. Litz wire is similar to stranded wire, except each individual strand is electrically insulated. This dramatically increases the effective area of the wire in AC applications and has almost no effect in DC applications. However, it can be a bit pricier and does have a worse packing factor, which is why we don't see Litz wire all over the place. Also, because the strands are more individual, it's possible to change the cross-sectional shape to improve the packaging trade-off and get a slightly better fill factor. Here's a snippet from a catalog of different wire types. The selection process is basically dominated by operational frequency, which dictates how thin each strand needs to be. One can also select their wire based on desired fill factor and shape. The last type of efficiency loss that we'll briefly touch on is bearings, as they are the main mechanical loss of the motor. Poor bearing selection can reduce efficiency by up to 5% due to inertia and high friction. For this, some manufacturers turn to ceramic bearings, which can be more efficient, but can also tend to be less consistent. For reliable applications, high-efficiency steel ball bearings are affordable and pretty easily attainable, and have very competitive rolling resistance to ceramic bearings. Motors are more often thermally limited than anything else. Even with the most efficient materials available, everything in the motor is producing heat, including the laminations, the coils, the bearings, and even the magnets themselves. As a result, temperatures of an in-hub solar car motor can realistically reach above 100 degrees Celsius if not kept in check. The biggest impact of this is on the magnets. Magnets are pretty stable at low temperatures, but as they heat up, the internal magnetic domains become a bit loose, meaning that they can lose their inherent magnetization. Unfortunately, this type of damage is permanent for the motor and cannot be fixed without replacing the magnets. The other big concern is the temperature of the wire. If the insulation of any individual strand of the wire burns up, the short circuits can be catastrophic, causing a fire or blowing out the motor controller. Lastly, the excessive temperatures can also warp the laminations and ruin the annealing process, which we'll talk about shortly. This failure mode tends to be a bit less common, but can have very strong temporary effects and can leave permanent damage if not noticed. As the laminations warp, the flux paths change, which can further increase heat production. This leads the motor into a state of near thermal runaway. We've covered a good portion of the steps to designing a motor, but how do we actually do it in practice? Here we're going to go over a few simulation and manufacturing techniques required to hop into motor design. Going back to our big concept map, we can see that we're starting to near the bottom, that we have brushed over quite a bit. We're now going to talk about simulation using FEA methods. To actually design the stator and rotor, we turn to finite element analysis, or FEA for short. Programs such as ANSYS Maxwell numerically solve Maxwell's equations over the individual pieces of a meshed model to develop a very detailed map of the electromagnetic fields. It can also approximate things like temperature. Here, we can see what the mesh looks like in the solver. Through ANSYS Maxwell, we are particularly looking at things like the field density in all parts of the motor to avoid saturation, and we can also look at transient and ripple curves of torque, current, speed, back EMF, and a few others. Here's a nice visualization of a Maxwell simulation. The color of the arrows indicate the magnetic field strength, allowing the user to view areas of high flux density and potential saturation. We can also see the exact flux path through each tooth of the stator and how it changes with rotor position. Note that this simulation only visualizes 1/8 of the motor. This is because Maxwell can automatically determine symmetries of the motor and remove them, saving on simulation time significantly. Each of these simulations can take something like 2 to 3 hours to run. Once we've got our motor designed and simulated, the last thing to look at is manufacturing. For making the laminations, water jetting or laser cutting is usually done for one-off or prototypes. Water jetting tends to have worse tolerance than laser cutting, but laser cutting can ever so slightly reduce efficiency if the laser melts the insulation layer. Both of these methods are quite slow, which drive costs significantly. In fact, manufacturing the stator and rotor are usually the most expensive parts of the motor. A set of stator laminations for a solar car can easily cost upwards of $6,000. For high volume production, stamping is always the way to go. It is much faster and cheaper after the tool is made. However, it does have the worst tolerance specs, meaning that proper tolerance analysis is required for carefully controlling the stacking process and controlling the air gap size. Once the laminations are cut, they are usually annealed. Annealing is a process in which the material is heated and cooled in a controlled environment in order to control the mechanical and magnetic properties. In general, annealing makes the material more ductile, which makes it better for forming, but simultaneously reduces yield and tensile strength. In the case of electrical steels, it is all but essential to align magnetic domains and remove excess carbon to get the small hysteresis curves mentioned for efficient magnetization. With the theory, design, and manufacturing portions wrapped up, we'll tie it all together by looking at a specific motor to see how these concepts show up in practice. Here's the last snippet of our map to see which parts we did and did not cover in this talk. For our summary example, we're going to look at some design decisions that can get a solar car motor up to the 95 to 98% efficiency range. After running through a torque and power analysis, most of these motors tend to run around 2 to 3 kilowatts and can weigh less than 20 kilograms. Very thin, non-oriented steel keeps the hysteresis and eddy currents minimized. Since solar car motors operate at lower speeds, the Litz wire is often left out in order to get a better fill factor, providing an overall net improvement on electrical resistance losses. Something that we didn't touch on was the different grades of magnets, but the N52 grade neodymium magnet is usually the best here for providing the highest field density possible. Ceramic or low friction steel ball bearings are common, and an air gap under 1 mm is easily maintained without the need for a composite sleeve. Since electrical noise can be a bit of an issue, resolvers are more reliable and can be worth the extra cost for low quantity units. While a motor with these specifications can cost upwards of $9,000 each, the near 100% efficiency is easily achievable. Here's a picture of a Mitsuba M2096-3, one of the more common solar car motors, clocking in at around 95% efficiency. This motor sticks to the traditional Hall effect sensor, using a very clean PCB standoff system for mounting. Here we can see the ultra-thin nickel lamination stacked very tightly, all bolted together with an evenly distributed bolt pattern. Several forms of insulation are used to protect the coils, including these plastic cages around the stator teeth. Other common methods are using Nomex paper or dipping the whole stator in a light resin before winding. Nice, thick, solid core wires keep resistance down and provide a good fill factor, looking to be somewhere in the mid to high 60% range. So that's it, a pretty dense and not even very extensive walkthrough of motor design. You can probably see by now that designing a motor is a huge task, but a very rewarding one. I would like to thank Dylan, Bernhard, and Meaty from the ENPH Project Lab for helping guide me through the project, the alumni from the Stanford Solar Car Project, Sam and Nathan, for providing a ton of information and helpful resources, and Dr. Jackiewicz from UBC for offering his expertise and helping me understand the heavy background and theory involved. Lastly, I'd like to thank you, the viewer, for listening. I hope you learned something valuable, and I hope you have a wonderful day.